Welcome to the Sleepy Scholar. It's lovely to have you here tonight. So before we begin, let me ask you the same thing I always ask. Where in the world are you listening from? Somewhere it's late, I'd guess. Maybe the lamp beside you is still on, throwing a little warm circle of light across the ceiling. Maybe you've got a blanket pulled up to your chin, or a cup of something gone half cold on the nightstand. Maybe you're on a train or a couch, or curled on your side in the dark with one ear free. Wherever you are, whatever the hour, settle in. You don't have to do anything tonight. You don't have to follow every thread. You don't have to remember a single word of it in the morning. You only have to be here, soft and still, and let the words drift over you like warm water. And if you enjoy these slow journeys, if you'd like more nights like this one, a quiet like and a subscribe really do help this sleepy little channel keep going. Small creators like me lean on that more than you'd think. And to those of you who already subscribed, who come back night after night and let me keep you company in the dark, thank you. Truly, it means the world. But there's no pressure here, none at all. You just rest. Now, I should warn you about tonight's subject because it's a big one. It's strange and it's beautiful, and it's the kind of thing that if you let it, could keep your mind turning over and over in the dark when it ought to be drifting down towards sleep. So I'll make you the deal I always make. I'll try my very best not to make this so interesting that it keeps you awake. But if I fail, if you find yourself lying there an hour from now still wide-eyed and wondering about the shape of the universe, well, at least you'll have learned something lovely. A fair trade, I think. So let's begin. Slowly, gently, one small mystery at a time. Here is something true, something happening to you right now as you lie there, as you breathe in and out and feel the weight of the blanket and the quiet of the room. You feel perfectly still. The bed isn't moving. The lamp isn't moving. The whole room is holding its breath around you, calm and motionless and safe. But you are not still, not even close. Right now, this very second, the entire galaxy you live in, the whole Milky Way, every star you've ever seen, and 100 billion more you haven't, all of it together, is falling through the dark at 600 kilometers every single second. Not 600 kilometers an hour, 600 kilometers in the time it takes to say the word second. That's a little over 2 million kilometers an hour. You, your bed, your warm little room, the ground beneath your house, the sun in the sky, the planets, the whole spinning wheel of stars we call home. All of it is racing through the universe faster than you could ever feel, faster than you could ever picture, toward a single direction in the sky. And here's the part that makes it strange. Here's the part that, even after a lifetime of studying it, still makes the people who do this for a living go quiet for a moment. We don't fully know what's pulling us. There's something out there, something enormous. Something sitting in a particular patch of sky, drawing us toward it the way a deep valley draws a river downhill. And for a long time, the whole story seemed to be just that. A great unseen weight, hidden in the dark, tugging our entire galaxy toward it. People even gave it a name that sounds like it belongs in a fairy tale or a nightmare. They called it the Great Attractor. But the truth, the real truth that scientists slowly uncovered over the last few decades is so much stranger and so much gentler than a monster in the dark. Because it turns out we are not only being pulled, we are also being pushed. About half of that great rushing motion, half of our 600 kilometers a second, isn't a pull toward anything at all. It's a push, a shove from behind. And the thing doing the shoving isn't a great mass. It isn't a giant. It isn't a monster. It's a void, an emptiness, a vast region of almost perfect nothing, sitting on the opposite side of the sky, and somehow, impossibly, that nothing is pushing us away. Now I know how that sounds. I know it sounds like I've made it up, like I'm just trying to keep you awake after all. How can nothing push you? How can emptiness do anything at all? Hold that question gently in your mind, like a smooth stone in your palm. We'll come back to it much later when the time is right, and I promise it will make a beautiful kind of sense. For now, just let it sit there, a push from nowhere, pulling half our weight. No need to solve it tonight. So that's where we're going. That's the journey. We're going to drift slowly out, away from your bed, away from this room, away from the Earth and the Sun and even the galaxy, all the way out to the largest things that exist. And we're going to ask the oldest, simplest question there is: what's out there? And why is it pulling us? And why, after all this time, can't we see it? But first, I think we have to answer a smaller question, a quieter one. And it's this: if we can't see the thing that's moving us, how on earth do we even know that we're moving at all? Because that's the curious thing, isn't it? You feel still. I feel still. The Earth seems to sit calmly in space. The stars seem fixed in their patterns, the same constellations our ancestors named thousands of years ago. So how could anyone possibly measure that the whole galaxy is rushing through the dark at 600 kilometers a second? What could you even measure it against? There are no mile markers in space, no signposts, no fixed wall to clock yourself against as you fly past. And the answer to that, the answer is one of the loveliest things I know. The answer is that we measured our speed against the oldest light in the universe. Let me explain that slowly, because it's worth lingering on. A very long time ago, longer than you can really hold in your head, the universe was young. And when it was very young, it was hot. Not warm like a summer day, not hot like a fire. Hot like the inside of a star. Hot enough that the whole universe glowed. The entire cosmos, everywhere, all at once, was filled with a furious, brilliant light. There was nowhere dark, there was nowhere cool, just light, everywhere, pressing in on itself. And then, as the universe grew, it cooled. The way a fresh loaf of bread cools when you take it out of the oven, the way a cup of tea cools when you leave it on the counter. Slowly, gently, over an unimaginable stretch of time, that ferocious early glow faded and stretched and dimmed, but it never went out, it never disappeared. It's still here, it's still falling on you right now, tonight, in your dark and quiet room. That ancient light has a name. We call it the cosmic microwave background, which is a mouthful, I know, so let me just give you the simple picture. Think of it as the afterglow of the beginning, the faint, cooled down embers of the fire the universe used to be. It's everywhere. It comes from every direction in the sky, an even gentle hum of warmth, the most distant and the most ancient thing we can ever detect. When you look at it, you are looking at the universe as a newborn, the oldest snapshot there is. Now here's where it gets beautiful. That afterglow is almost perfectly even. Almost. Look in any direction, and it's nearly the same temperature, this faint, faint warmth left over from the dawn of everything, but not quite, because we are moving through it. And when you move through something, even something as gentle as this ancient sea of light, something changes. Think of standing in a soft, steady rain that's falling straight down, perfectly even, all around you. If you stand still, the rain hits you the same on every side, but the moment you start to walk forward, the rain starts hitting your face a little harder. You're walking into it, and behind you, the rain feels a little lighter because you're moving away from it. You haven't changed the rain at all, you've just started moving through it, and that motion shows up as more in front, less behind. That's exactly what happens with the oldest light in the universe. Because our galaxy is rushing in one particular direction, the ancient afterglow looks the tiniest bit warmer in the direction we're heading. We're moving into it, so it piles up a little, the way the rain piles up on your face. And in the opposite direction, the direction we're moving away from, it looks the tiniest bit cooler, warmer ahead, cooler behind, a faint, lopsided pattern stamped across the whole sky. Scientists have a word for that lopsidedness. They call it the dipole, which just means it has two poles, two ends, a warm end and a cool end, like the two ends of a magnet. The CMB dipole, the warm spot in the sky that shows us which way we're going. And here's the thing that always stops me. The difference is unbelievably small. We're not talking about one side of the sky being hot and the other cold. We're talking about a difference of about 3 1/3 thousandths of a degree. 3.36 millikelvin if you want the exact number, which is a fancy way of saying a tiny, tiny fraction of a single degree. Smaller than you could ever feel, smaller than almost anything you could ever measure with your hands or your skin or any ordinary tool. A whisper of a difference painted faint across the entire sky. And yet from that whisper, from that almost nothing, scientists worked out exactly how fast we're moving and in exactly which direction, 600 kilometers a second toward one particular patch of sky. That's how we know. Not from feeling it, not from seeing the thing that pulls us, but by reading the faint, warm tilt in the afterglow of the beginning of time, like reading which way the wind is blowing by the lean of the grass. It took remarkable machines to read something so faint. The first to truly catch it was a spacecraft called COBE, back in the 1990s, with instruments that listened to that ancient light with extraordinary patience and care. And then, years later, a far more sensitive spacecraft called Planck looked again, in much finer detail, in the years leading up to 2018, and confirmed it. Yes, the pattern is real. The tilt is there. We are moving, and this is how fast, and this is where to. Isn't that a wonderful thing to know as you lie there? That somewhere, patient people built machines to listen to the faintest warmth in the oldest light, and from a difference smaller than you could ever feel, they learned that you are flying through the cosmos at 600 kilometers a second, and they even learned which way you're pointed. There's something so tender about that. The universe doesn't shout its secrets. It whispers them, and we learn to listen very, very carefully. Now, I keep saying we. I keep saying our galaxy is moving. But I should be a little more careful, a little more precise, because the truth is even lovelier when you see it properly. It isn't just the Milky Way that's moving, it's our whole neighborhood, our whole little family of galaxies, all moving together, all falling in the same direction at once. Because the Milky Way doesn't drift alone through the dark. It has companions. It belongs to a small cluster of galaxies that all hang together, bound by their own gravity, traveling as a group. Astronomers call this little family the local group. A modest name for something so vast, but I rather like it. It's homey, it's the local group, our part of town. And who lives in our part of town? Well, the Milky Way, of course, that's us. The great spiral wheel of stars we call home. And then there's our big sister, Andromeda, sometimes called M31, an even larger spiral galaxy that you can actually see with your own eyes on a very dark night, a faint smudge of light that is, in truth, 1 trillion suns. The Milky Way and Andromeda are the two giants of the neighborhood, the two big houses on the street. And gathered around them, drawn in close by their gravity, are around 80 smaller galaxies. Little ones, dim ones, dwarf galaxies orbiting the big two like children playing in the yard. 80 or so of them, give or take, all clustered together. That's the local group. The Milky Way, Andromeda, and their roughly 80 smaller companions, our cosmic family. And the remarkable thing, the thing worth holding on to, is that the whole family is moving together. The entire local group, all of it at once, is streaming through the universe at that same 600 kilometers a second, about 2.2 million kilometers an hour, all of us falling in the same direction, toward the same hidden thing in the sky. It's a strange comfort that we're not falling alone. We're falling with our whole family beside us, our big sister Andromeda and all our little cousins, all of us carried along together by the same great current, all leaning the same way like passengers on a ship that's turning, none of us feeling the motion at all. And remember, we measure this motion against the oldest light there is. When we say the local group is moving at 600 kilometers a second, we mean it's moving relative to that ancient afterglow, relative to the gentle, even sea of light left over from the beginning. The afterglow gives us something to measure against. It's the closest thing the universe has to a stillness, a fixed background, a way of saying this is what not moving would look like. And against that stillness, our whole family is rushing forward all together toward one spot in the sky. So now we know two things. We know that we're moving fast, all of us together, and we know how we figured it out by reading the faint, warm tilt in the oldest light. But we still don't know the most important thing, the thing the whole journey is really about. We don't know what's out there. We don't know what we're falling toward. And here is where the real mystery begins. Because you'd think, wouldn't you, that the answer would be simple. If something that enormous is pulling on our entire galaxy, hard enough to fling us through space at 600 kilometers a second, then surely we could just look in that direction and see it. Surely something with that much pull, that much weight, would be blazing away in the sky, impossible to miss. You'd just point your telescope toward the warm spot, toward the direction we're falling, and there it would be, the thing that's pulling us, the answer. But when astronomers turned their telescopes toward that exact spot in the sky, toward the direction we're rushing, they ran into a wall they could not see past, no matter how hard they tried. And the wall is us. This is the part I find almost unbearably beautiful in its irony. The reason we can't see the thing that's pulling our galaxy is that our own galaxy is standing in the way. Let me paint it for you. Picture the Milky Way not from inside it, but from far away, the way you'd picture it in a painting. It's a great flat disk, a vast wheel of stars, with a thick, bright bulge in the middle and graceful arms spiraling outward. Now here's the trouble. We don't live above that disk looking down on it from a comfortable distance. We live inside it. We're embedded right in the flat plate of the wheel, partway out along one of the arms. And that means that when we look out into the universe, in most directions we have a clear view. Up out of the disk, down out of the disk, off into the dark, where the sky is open. But in one direction, the view is a disaster. When we try to look out along the plane of the disk itself, straight through the thickest, busiest part of our own galaxy, we're looking through everything, through countless stars crowded close together, through thick clouds of gas, and worst of all, through dust. Enormous dark lanes and banks of cosmic dust, fine soot strewn through the disk, dimming and smothering the light from anything behind it. It's like trying to look out a window at a distant mountain, except the window is fogged and grimy and packed with smoke, and there are 1,000 bright lamps crowded up against the glass, dazzling your eyes. You can't see through. The mountain might be right there, enormous, looming, but you'd never know because your own dirty, crowded window is in the way. Astronomers have a name for this troublesome region, this stretch of sky where our own galaxy blocks the view, and it's a wonderful name, an almost poetic one. They call it the Zone of Avoidance. The Zone of Avoidance. The part of the sky that galaxies seem to avoid. Not because galaxies are truly absent there, but because we simply can't see them through the murk of our own Milky Way's disk. It's a band stretching right across the sky, following the line of the galactic plane, and it covers a startling amount of the heavens. Somewhere between 10 and 20% of the entire sky is lost to us this way. Imagine that. A tenth, maybe a fifth, of everything out there simply curtained off, hidden behind the dusty bulk of our own home. And this isn't some recent discovery, some modern puzzle. People noticed it a very long time ago, back when telescopes were far simpler, and astronomers counted galaxies by hand, one by one, by eye, on photographic plates. Back in the 1930s, the astronomer Edwin Hubble, the very same Hubble the Great Space Telescope is named after, was painstakingly counting galaxies across the sky, trying to map how they were spread out. And he noticed something strange. There was a band, a stripe, running right along the plane of the Milky Way, where almost no galaxies appeared at all. A clear, empty avenue cutting across his maps. Now Hubble understood what was happening. He knew the galaxies weren't really missing. He knew they were there behind the curtain, hidden by the dust and the crowding of our own galaxy's disk. He called it the Zone of Avoidance, this region the galaxies seem to shy away from, and the name stuck. Nearly a century later, we still use it, the Zone of Avoidance, the blind spot in our view of the universe. And here is the cruelest, most exquisite twist of the whole story. Of all the directions the great pull could have come from, of all the places in the wide open sky where that hidden mass could have sat, where do you think it lies? It lies almost exactly behind the densest, darkest part of the Zone of Avoidance. The thing that is pulling our entire galaxy, the great unseen weight we're falling toward at 600 kilometers a second, sits right down low against the plane of the Milky Way, in the very direction where our own galaxy's dust is thickest, where the crowding is worst, where the curtain is heaviest. Of all the places it could have hidden, it hid in the one spot we are least able to see. It's almost as if the universe were teasing us, as if it had taken the single most important object in our cosmic story and tucked it away precisely behind the one wall we can't look through. So that, my friend, is the puzzle we're left holding tonight. We know we're moving. We know how fast, 600 kilometers a second. We know which way toward one particular patch of sky. We know how we figured it all out by reading the faint, warm tilt in the oldest light in the universe. And we know now exactly why we can't simply look and see what's pulling us. Because our own home, the Milky Way itself, the bright, crowded, dusty disk we live inside, is standing squarely in the way. The thing we're falling toward is hidden behind the one obstacle we can never move aside, ourselves. And so we arrive at a question. The first real question of the night, the one I want you to carry softly with you as you start to drift, it's this. If the thing we're chasing is hidden behind a wall we cannot remove, behind the dust and crowding of our own galaxy, then how do you study it at all? How do you map a thing you cannot see? How do you weigh something hidden behind your own front door, measure a mountain you can never glimpse through the fog? It seems impossible. It seems like a locked room with no key. And yet patient people did find a way in. They found ways to see through the curtain after all, to slip past the dust, to catch the faint signals of whatever lies on the other side. It took clever instruments and stranger kinds of light than your eyes will ever know, light that passes through dust the way a voice passes through a wall. And bit by bit, signal by faint signal, they began to draw a picture of the hidden thing. They gave it a name. They found its heart. And then, just when they thought they had it, they discovered that the thing they'd named couldn't possibly be strong enough to explain our speed, that there had to be something else, something larger, something farther, lurking beyond it in the dark. But that is a story for a little later. For now, just rest with the wonder of it. You are lying still and safe in your warm little room, and yet you are flying through the cosmos at 600 kilometers a second, carried along with your whole galactic family, falling towards something vast and hidden, something even the cleverest people on Earth are still working to understand. There's no need to solve it tonight. There's no need to do anything at all. The universe has been falling this way for billions of years, and it will keep falling long after you've drifted off to sleep. So let it. Let the great current carry you. We'll follow where it leads, slowly, gently, in just a little while. But before we follow it, let's go back to the very beginning of this strange knowledge. Let's answer the simplest question first. How does anyone know we're moving at all? You're lying down. The room is still. The bed isn't shaking. By every sense you have, you and the whole Earth are perfectly at rest. So how could anyone possibly claim we're racing through space at 600 kilometers a second? The answer is one of the most beautiful tricks in all of science, and it has to do with the oldest light there is. A very long time ago, when the universe was young and hot and crowded, the whole of space was filled with a kind of glow. Think of it like the warmth that lingers in a room after a fire has burned down, except this fire was the birth of everything, and the room was the entire cosmos. As the universe expanded and cooled over billions of years, that glow stretched and faded and softened until it became something we can still detect today, all around us, in every direction. We call it the cosmic microwave background, the afterglow of the Big Bang. The oldest light in existence, set free when the universe was only a few 100,000 years old. And here's the lovely part. That ancient light is almost perfectly even whichever way you point your instrument. It looks just about the same temperature, a faint and steady warmth filling all of space. Almost. Because when scientists measured it very, very carefully, they found something. The afterglow looks just a tiny bit warmer in one particular direction and just a tiny bit cooler in the opposite direction. Now, why would that be? Imagine you're walking through a gentle, even rain on a windless day. The rain falls the same all around you. But the moment you start to run, the rain feels like it's coming harder against your face and softer against your back. You haven't changed the rain at all. You've only changed yourself by moving through it. The drops hit your front more often simply because you're rushing toward them. The oldest light works the same way. When you move through that sea of ancient glow, the light ahead of you in your direction of travel gets gently bunched up and looks a little warmer. We call that a blue shift, and the light behind you stretches out and looks a little cooler. A red shift. The afterglow itself hasn't changed. It's perfectly even. We are the ones who are moving, and our motion paints that faint, warm and cool pattern across the whole sky. This pattern has a name. The CMB dipole. Two poles, one warm, one cool, like the two ends of a magnet, drawn across the heavens by nothing more than our own speed. And the difference is astonishingly small. The warm side is hotter than the cool side by only about 3 1/3 thousandths of a degree, 3.36 millikelvin to be exact. A whisper of a temperature difference far too faint for any human sense, far too subtle for the eye or the skin. And yet, from that whisper, that tiniest of asymmetries in the oldest light in the universe, scientists can read our speed directly, like reading the wind from the lean of the grass. It was a satellite called COBE that first measured this with real precision, back in the early 1990s, with instruments named FIRAS and DMR, listening to the faint warmth of the early cosmos. And decades later, a newer mission, the Planck satellite, confirmed it again in 2018 with even sharper eyes, reading that same gentle lean in the ancient light. The number held. We are moving. There's no doubt about it now. So how fast? And toward what? Here is where it gets quietly staggering. It isn't just the Earth moving or even just the Sun. It's our whole neighborhood, our galaxy. The Milky Way doesn't drift alone through the dark. It travels in a family. We call it the local group, a small cluster of galaxies bound together by gravity, drifting through space as one. There's us, the Milky Way, and our great companion, Andromeda, sometimes called M31, that vast spiral wheeling toward us across the gulf. And around the two of them, scattered like children around two parents, are roughly 80 smaller galaxies, little dwarf companions, faint and close, all held in the same gentle gravitational embrace. And this whole family, all 80-something of us, the Milky Way and Andromeda and all our little siblings, is moving together. Measured against that ancient glow, against the rest frame of the afterglow of the Big Bang, the entire local group is falling at about 600 kilometers every single second. Let that number settle softly over you the way a blanket settles, 600 kilometers a second. That's around 2.2 million kilometers an hour. While you lie here, perfectly still, breathing slow, your whole galaxy and everyone in it is being carried across the cosmos faster than you could ever picture. And you feel none of it. There's no wind, no rush, no shudder in the floor. Just stillness and warmth and the quiet motion of everything at once. So now we know the speed, we know the direction. We're falling, all of us together, toward one particular patch of sky. And naturally, the next question is the one that's been waiting in the dark this whole time. What's there? What lies in that direction, pulling on our entire galactic family with enough force to drag us along at 2 million kilometers an hour? You'd think that would be the easy part. Point your telescope where we're heading and look. Surely something that massive, something that powerful would blaze out at us, obvious and bright. But this is where the universe plays its strangest and most fitting trick. Because when astronomers turn to look in the direction we're falling, toward the region in the sky near the old constellations of Centaurus and Hydra, they found their view blocked. Not by distance, not by darkness, but by something far closer to home, by us. You see, our own galaxy, the Milky Way, isn't just a scattering of distant stars in the night sky. We live inside it. We're tucked into one of its spiral arms, looking out through the whole flat disk of it. And that disk is crowded, thick with stars, yes, but more than that, thick with dust and gas, great dark clouds of it, drifting between the stars like fog rolling across a valley floor. And that fog has a way of swallowing light. Visible light, the kind your eyes use, simply can't push through it. It gets absorbed, scattered, lost. So when you look out toward the heart of our own galaxy, toward that dense, dusty band that arcs across the night, you can't see what's behind it. Anything out there in deep space, any galaxy, any cluster, any vast hidden structure sitting beyond the Milky Way's disk is hidden from view, blotted out by the dust and the crowding of our own home. Astronomers gave this blind spot a name long ago. They call it the Zone of Avoidance, a fitting, almost wistful name. It's the part of the sky where galaxies seem to avoid us, where the catalogues go strangely empty, not because nothing's there, but because we simply can't see through to it. It stretches across a wide band of the heavens, somewhere between 10 and 20% of the entire sky. A tenth or more of everything out there, curtained off behind our own front porch. This isn't a new discovery either. Almost a century ago in the 1930s, the astronomer Edwin Hubble, the very same Hubble the Great Telescope is named for, was painstakingly counting galaxies across the sky. And he noticed it then. There was this band, this zone, where the galaxies simply stopped appearing, a gap in the cosmos that wasn't really a gap at all, just a place we were blind to. And here is the exquisite irony at the heart of this whole story. The thing pulling our entire galaxy across the universe, the great hidden mass we're all falling toward, sits almost exactly behind the densest, dustiest part of the zone of avoidance. The single most important thing in our cosmic neighborhood, the destination of our long fall through the dark, and it just happens to lie in the one direction we can't see. Hidden, of all things, by our own home standing in the way. So there we are. The map we carry is incomplete. The census of the universe has a hole in it, right in the most consequential place. And yet, astronomers didn't simply accept that. They went looking anyway. And what happened next is one of the quiet masterpieces of modern science. It begins in 1988. 7 astronomers, working together across different institutions, set out to do something that sounds almost comically ambitious on its face: map the motion of the universe around us. Not just where things are going, and how fast. Their names were Donald Lynden-Bell, Sandra Faber, David Burstein, Roger Davies, Alan Dressler, Roberto Turlevich, and Gary Wegner. 7 people, and they would come to be known affectionately as the 7 Samurai. The nickname has a certain romance to it, doesn't it? 7 astronomers armed with telescopes and data, and a stubborn refusal to accept that some things simply can't be known, riding out to face a cosmos that had been keeping a secret. Their method was patient and careful. They chose to study elliptical galaxies. Elliptical galaxies are the great old ones, smooth and rounded and comparatively simple in their structure, without the elaborate spiral arms of a galaxy like ours. And for their purposes, they had a beautiful property: they behave like calibrated instruments. There's a relationship, a reliable one, between how bright an elliptical galaxy intrinsically is and how fast its stars are moving around inside it. The faster the internal motion, the more massive and luminous the galaxy. This relationship is called the Faber-Jackson relation, named after Sandra Faber herself and her colleague Robert Jackson, who worked it out a decade earlier. It's the kind of elegant, underlying law that the cosmos seems almost to have placed there for astronomers to find. Because here is what that relationship allows you to do. If you can measure the internal stellar motions of an elliptical galaxy, which you can from its spectrum by watching the slight broadening of its spectral lines, you can estimate how intrinsically bright it ought to be. In other words, what the galactic equivalent of the wattage of the light bulb is. Then you can compare that to how bright it actually appears from Earth. And from the difference, you can work out exactly how far away it truly is, independently of its redshift. This matters enormously because if you then look at the galaxy's redshift, how fast it appears to be receding from us due to cosmic expansion, and compare it to the distance you've just calculated independently, any discrepancy between those two numbers tells you something. It tells you that the galaxy has a peculiar velocity, a motion over and above the cosmic expansion, a motion caused not by the expanding universe but by gravity pulling it somewhere. The 7 Samurai did this for approximately 400 elliptical galaxies spread across a large region of sky, 400 independent measurements, 400 little probes, each one an indirect finger pointing in a direction. And when they laid out the results, when they looked at where all of the discrepancies pointed, something astonishing emerged. The galaxies weren't moving randomly, they were streaming. Almost all of them, regardless of where they were in the sky, were drifting coherently in one direction. Like a vast, slow current in the deep ocean, flowing toward a single region. Not rushing, in any sense we'd find dramatic, but with a steady, relentless purpose, the way a river has purpose even when you can't feel the current by standing in it. Everything was moving together towards something in the direction of the constellations Centaurus and Hydra. There was something there, something massive, enormously, invisibly massive, generating enough gravity to set hundreds of galaxies into motion, and yet it sat squarely behind the zone of avoidance, hidden in precisely the direction our own galaxy chose to obscure. Lynden-Bell and the team named it the Great Attractor. And it is a name that does something to the imagination, doesn't it? Not just a cluster, not just a supercluster, but an attractor, a gravitational destiny. The word lands differently than a catalogue number. It has weight. The Great Attractor sits, by their estimates, somewhere between 150 and 250 million light-years from us, in the direction of Centaurus and Hydra, near what astronomers describe in galactic coordinates as roughly L equals 320 degrees, B equals 0 degrees. That second number, B equals 0, is important. It's the galactic latitude, the measure of how far something sits above or below the plane of the Milky Way's disk. 0 means right on the equator, right in the band, right behind the thickest part of the zone of avoidance. You couldn't have placed it more inconveniently if you'd tried. And so for years, the Great Attractor occupied a peculiar place in astronomy, definitively real, definitively named, and almost entirely unseen. The evidence for it was irrefutable, hundreds of galaxies streaming toward a point. The bulk flow measured in the data as clearly as a river's direction can be measured by watching leaves on the water. But the thing itself, the mass at the bottom of the gravitational slope, was behind the curtain. Here is where patience begins to pay off. Because the curtain was not, it turned out, completely opaque. Light comes in many wavelengths. Visible light, the kind our eyes evolved to see, the kind that carries the colors of sunsets and the pale glow of distant galaxies in a telescope eyepiece, is only one narrow sliver of the electromagnetic spectrum. And dust is unkind to visible light. Dust grains scatter and absorb it, preferentially, at those shorter wavelengths. The thicker the dust, the more visible light gets eaten up before it can reach you. In the densest parts of the zone of avoidance, the extinction in visible light can reach many magnitudes, which in practice means the light is dimmed by factors of millions or more. No visible light telescope, no matter how powerful, was going to see through that. But longer wavelengths fare differently. Radio waves, for instance, slip through dust almost entirely unimpeded. They don't interact with the dust in the same way. They pass through it the way sound passes through a wall that light cannot penetrate. And there is one particular radio wavelength that turned out to be an extraordinary gift for this problem. The 21 centimeter line, 21 centimeters. The wavelength of electromagnetic radiation emitted by cold, neutral hydrogen gas when the electron in a hydrogen atom undergoes a small, spontaneous flip in its spin state. It's a subtle quantum mechanical transition, and in any one hydrogen atom it happens very rarely. But hydrogen is the most abundant element in the universe. The universe is full of it. Clouds of neutral hydrogen gas, enormous and diffuse, hang between galaxies, within galaxies, scattered through the cosmos in vast traceries that are all but invisible in the optical band, but ring out clearly at radio frequencies. And because they ring out at exactly 21 centimeters, any radio telescope tuned to that wavelength can detect them. You can think of it like this. Imagine you're trying to see a scene through a very thick, very dirty window. In visible light, you can barely make out shapes, but now imagine the scene emits a kind of sound that passes through glass with no trouble at all. Suddenly you can hear everything that was visually hidden. The 21 centimeter line is that sound. Astronomers use this. In a series of surveys, most significantly the H.I. Parkes All-Sky Survey, known as HIPASS, they pointed radio telescopes at the zone of avoidance and listened for hydrogen at 21 centimeters. And the galaxies behind the dust began to reveal themselves one by one, announcing their presence through their neutral hydrogen gas, even where their starlight was hopelessly buried. It wasn't only radio waves that helped. Near-infrared light, slightly longer in wavelength than visible light, also penetrates dust considerably better, though not as dramatically as radio. The 2-micron all-sky survey, the 2-mass survey, mapped the whole sky at near-infrared wavelengths and found thousands of galaxies lurking in the zone of avoidance that optical surveys had entirely missed. You look through the same region of sky in visible light, and you see a few smeared stars and a dark, obscuring tangle of our own galaxy's material. You look in near-infrared, and suddenly galaxies emerge from the murk, revealed like figures stepping out of a fog. X-ray observations contributed too. Galaxy clusters, those enormous collections of hundreds or thousands of galaxies bound together by gravity, contain vast amounts of very hot gas between their members, gas so hot it glows at X-ray wavelengths. X-rays, for similar reasons to radio waves, are far less subject to dust extinction than optical light. So X-ray satellites, looking toward the zone of avoidance, could detect the hot intracluster gas of large concentrations of galaxies, even when the galaxies themselves were optically hidden. What emerged from all this multi-wavelength archaeology, this patient use of every observational tool available, was a gradually clearing picture. And in that picture, as the curtain thinned, if not fully lifted, one object stood out above the rest. The Norma Cluster, officially catalogued as Abell 3627, located approximately 220 million light-years away, right in the heart of the Great Attractor region, right at the edge of what the Zone of Avoidance conceals from optical view. In 1996, Renée Kraan-Korteweg and her collaborators brought it into something approaching clarity. Kraan-Korteweg, whose career has been in many ways dedicated to the heroic project of mapping what lies behind the curtain of our own galaxy, helped establish the Norma Cluster as the likely dense core of whatever was pulling us. The most massive structure visible in that direction. The thing closest to a face on what had been only a silhouette. And it is an impressive face. The Norma Cluster is one of the largest galaxy clusters in our cosmic neighborhood, a vast gravitational knot of galaxies, hundreds of members in the cluster itself, plus all the surrounding filaments and groups that trail away from it in every direction. If you could somehow lift our galaxy out of the way, remove the obscuring disk of the Milky Way and see the Great Attractor region plainly, the Norma Cluster would dominate the view the way a mountain dominates a valley. It's enormous, dense, a genuine gravitational giant. And yet, here is where the story shifts. When astronomers carefully estimated the mass of the Norma Cluster, when they added up all the galaxies they could see and applied the standard physics to infer the dark matter holding it together, the number they got was large. Very large, but it was not large enough. Run the calculation backward from the bulk flow measurement, the one the Seven Samurai made so carefully with their 400 elliptical galaxies, and ask, how much mass would you need at that location to accelerate the local group to 600 kilometers per second? The Norma Cluster, impressive as it is, falls short, significantly short. The gravitational budget doesn't balance. Something was missing. This is the moment in the story where the mystery deepens rather than resolves. You've identified the hidden region. You've pierced the obscuring veil with radio waves and infrared and X-rays. You've found the massive cluster lurking there in the dust. You've named the Great Attractor and given it a face, and then the arithmetic tells you, this still isn't enough. The thing you found is real and it matters, but it isn't the whole answer. The named attractor, for all its genuine enormity, is not the gravitational culprit you were looking for. Not entirely, not even mostly, as it would later turn out. Before we follow that thread, though, it's worth pausing to lay one misconception gently to rest. Because the Great Attractor has, over the decades since Lynden-Bell and the Seven Samurai named it, accrued a certain dramatic folklore in popular imagination, You can find it described in breathless terms as a cosmic monster, as a supermassive black hole of unimaginable proportions, as a thing that devours galaxies, that is eating the universe from the inside out, that represents some kind of apocalyptic threat to everything we know. None of this is true. The Great Attractor is not a black hole. It is not a single, dense, singular object of any kind. There is no evidence whatsoever that it is a point source, a singularity, a swallowing mouth at the center of the cosmos. What the Seven Samurai found, and what subsequent observations have confirmed, is not a thing but a region, a broad, extended concentration of matter, much of it still being mapped, made up of clusters and groups and filaments, and the invisible dark matter woven through all of them, spread across millions of light years. The gravity it exerts is real and measurable and significant, but it is the gravity of structure, not of a monster. Think of it like a mountain range rather than a pit. A mountain range doesn't swallow anything. It doesn't consume or destroy, but if you pour water into a landscape shaped by mountain ranges, the water flows toward the valleys between them, follows the topography, drains toward the lowest available point. Gravity over cosmological distances works something like that. The Great Attractor region is a high point of mass density, and the surrounding galaxies, including ours, flow toward it the way water flows downhill. Not sucked in violently, just drifting over billions of years along the shape of the gravitational landscape. And even that picture, the picture of galaxies draining toward the Great Attractor, the way water drains toward a basin, is incomplete, because the accounting problem remains. The Norma Cluster and the surrounding mass in the Great Attractor region explain part of our motion. They are genuinely pulling us. But when you work out the numbers honestly, when you're careful about what the bulk flow data actually says, it becomes clear that something further away, something even more massive, is also contributing, substantially contributing. The mystery deepens. The curtain was lifted a little. What was behind it was real and significant. And behind that there was something else. So what is it? Where does the rest of the pull come from? The answer lies much further away. Far beyond the Great Attractor, far beyond even the Norma Cluster, out at a distance that makes 220 million light-years seem almost cozy by comparison. There is a structure already partly identified and named decades ago, but only properly reckoned with in terms of its gravitational influence on us more recently. It goes by the name of the Shapley Supercluster. But we are getting ahead of ourselves. That belongs to the next part of the story, and it changes things significantly. For now, let's sit for a moment with what we have, because what we have is remarkable enough. Think about where we began. Edwin Hubble in the 1930s noticing a band of sky where the galaxies disappeared, a gap in the census that wasn't a gap but a blind spot. Then, half a century later, 7 astronomers studying the motions of 400 galaxies and detecting a coherent flow, a current running through the cosmic sea, pointing toward a hidden mass they could not see but could unmistakably feel, the way you can feel a wind's direction without seeing the air itself. They named it. They fixed its location in the sky, in the direction of Centaurus and Hydra, right at the equator of our own galaxy, in the densest part of the dust. They calculated its rough distance, 150 to 250 million light-years, and its rough mass, and they gave it the name that would carry the weight of the story ever after. And then the radio astronomers and the infrared surveys and the X-ray satellites went looking. They used wavelengths of light that the dust could not stop. They found galaxies behind the curtain. They found the Norma Cluster, massive and dense, anchoring that region of the sky. Renée Kraan-Korteweg and her collaborators spent years mapping what lies behind the Zone of Avoidance, that band of sky Hubble noticed as empty and that we now know to be full. Full of things hidden from us, simply because of the geometry of where we happen to live. And that geometry, that cosmic accident of our position inside a dusty disk has shaped the entire history of how we came to understand our own address. The thing pulling us is hidden by our home. The mystery is structural, not supernatural. There's something oddly humanizing about that, isn't there? All science has this quality if you look closely enough. The obstacles to understanding are never merely the difficulty of the universe. They are the difficulty of the particular position from which we happen to be looking. We see from inside, we see through our own structure. And what that structure blocks, we have to infer sideways with ingenuity, using the tools available to us, using 21-centimeter radio waves and near-infrared detectors and X-ray telescopes, looking up through our own galaxy's disk at the universe beyond. There is something almost meditative about that effort. The patient, cumulative work of looking harder, looking differently, using every available wavelength to see what visible light cannot reach. It took decades, it took many people, the Seven Samurai and Renée Kraan-Korteweg and many others working at it in overlapping generations. The map of what lies behind the zone of avoidance was not drawn in a single moment of discovery. It was assembled slowly, painstakingly, the way you might reassemble a broken object from its scattered pieces, each new observation adding one more fragment to the picture. And the picture, even now, is incomplete. As of only a few years ago, as recently as 2016 and 2017, new giant structures were still being found lurking in the zone of avoidance, hidden by the same dust, uncharted until recent surveys finally got a look at them. The Shapley Supercluster, discovered by Renée Kraan-Korteweg's team, is one of them. A vast structure about 800 million light-years away, also partly obscured by the zone of avoidance, announced to science in 2017. Another piece of the gravitational puzzle, another hidden giant in the dark. The map is not finished. That's worth staying with for a moment. This is not history. This is not a solved problem neatly filed away in textbooks. In our lifetimes, significant new structures contributing to the gravitational landscape of the cosmos we live in have been found and named. New answers to the question of what is pulling us and why we're moving the way we are still being assembled. The universe is older than any human civilization by an almost incomprehensible margin, and yet our map of even its nearest reaches is still being drawn. But let us return, for a moment, to that incomplete accounting, to the fact that the Great Attractor, the Norma Cluster, the mass we've identified and measured in that direction, is not enough to explain our motion fully. It is not enough. And that gap in the budget, that discrepancy between the pull we've measured and the mass we've found, points somewhere else. It points further. It points to a structure so massive that it dwarfs everything we've discussed so far, sitting further away in the same general direction, pulling on us with a gravity that reaches across nearly 650 million light-years of cosmic space. It points to the Shapley Supercluster. But before we drift there, and we will gently in the next part of this journey, there is one more thing to sit with about what we've covered tonight. One more layer to the invisibility. We've talked about two reasons the Great Attractor is hard to see. The zone of avoidance is one of them. The dust and gas and crowding stars of our own galaxy's disk blocking the optical light from whatever lies behind. A physical obstruction, a curtain made of our own home. Radio waves and infrared and X-rays can help, but they cannot fully lift it. The picture is clearer now than it was in 1988, when the Seven Samurai named the thing, but it is still partial, still obscured at its heart. But there is a second invisibility. And this one is deeper, in a way, more fundamental. It doesn't depend on dust or geometry. It wouldn't go away even if we somehow moved outside our galaxy and looked at the Great Attractor region with perfect clarity from every angle. The mass that constitutes the Great Attractor, the mass that constitutes Laniakea, the supercluster we are part of, the Shapley Supercluster beyond it, every large-scale structure in the cosmos is overwhelmingly, dominantly made of something that emits no light at any wavelength, no radio waves, no infrared, no visible light, no X-rays, nothing. It does not shine, it does not glow, it does not interact with the electromagnetic spectrum in any way we can detect. The only thing it does, the only handle astronomy has on it at all, is that it has mass, and mass means gravity, and gravity moves things, bends light, shapes structure. Dark matter, roughly 85% of all the matter in the universe. The gravity we are responding to, the gravitational slope we are sliding down, is largely the gravity of something we cannot directly see and have never directly detected. In this sense, the title of this story is doubly true. Something we cannot see is pulling us, but there are two distinct and separate reasons we cannot see it. The zone of avoidance is one, our own dust hiding a region of space behind a curtain. Dark matter is the other. The dominant mass component of the universe being inherently invisible, radiating no light, existing only as a gravitational presence woven through the cosmic web. If tomorrow somehow every dust grain in the Milky Way's disk were magically swept away and we could see the zone of avoidance in perfect optical clarity, we would see galaxies there. We would see the Norma Cluster. We would see filaments and groups of galaxies and the large-scale structure behind the curtain. And it would be astonishing, but we still would not be seeing most of what's pulling us. Most of it would still be invisible because most of it is dark matter, existing all around the luminous galaxies we can detect, holding them in place, making up the scaffolding on which the whole cosmic web is built. The luminous matter, the stuff that glows, the galaxies and gas clouds and stars that we see across the cosmos, all of that, everything we can point a telescope at and observe, is a kind of tracing. A smear of light painted over a much larger invisible architecture. The galaxies are like the foam on a wave, visible, dramatic, indicative of the wave's shape, but not the wave itself. The wave is the dark matter, and the dark matter is what's pulling us. This is perhaps the deepest strangeness in this whole story. We are being pulled at 600 kilometers per second toward a concentration of mass that is mostly invisible in two separate, independent, stacked ways. Dust hides its location from our telescopes. Dark matter makes up most of its actual substance. The thing is hidden twice over, and only the faintest indirect evidence of it, the coordinated drift of hundreds of galaxies, the slight asymmetry in the temperature of the Big Bang's oldest light, tells us it's there at all. And yet we know it's there. The evidence is as solid as evidence gets in astronomy. The measurements are independent, coming from different methods, different telescopes, different research groups. The Seven Samurai were not alone in finding bulk flows. Subsequent studies confirmed and refined their work. The picture has only grown clearer and stranger as we've added more observations, more wavelengths, more techniques. Here is a thought to carry with you as you settle in a little more deeply. Right now, in this moment, wherever you are part of a vast and coordinated motion that you cannot feel, cannot perceive, have no sensory access to whatsoever. You are drifting along with everything you can see in every direction, along with every galaxy in our local cosmic neighborhood, toward a gravitational focus that is hidden by our own galaxy and composed mostly of invisible matter. You are part of a flow. A stream of galaxies all moving together with the silent, unhurried purpose of water finding its lowest point. The Seven Samurai measured that flow. They traced it in the motions of 400 galaxies, and what they found pointed, clearly and unambiguously, to something in the direction our own galaxy has always hidden from us, something we have been approaching together for longer than any concept of time that human minds are scaled to hold. And we are still approaching it. And the story of what it actually is, what it's truly made of, and what lies beyond it, That is where we're headed next. But for now, let the 21-centimeter radio waves pass through the dust in your mind. Let the infrared surveys sweep the zone of avoidance. Let the Norma Cluster emerge slowly from the murk, enormous and ancient, partially visible, partially still hidden. Let the arithmetic of the bulk flow tell you quietly but firmly that there is more. More to find, more to the pull. There is always more. Because the Great Attractor, as it happens, is only the first layer, only the first waypoint on a much longer path. What lies behind it and beyond it and around it is stranger still. And the strangest part of all isn't even what's pulling us, it's what's pushing us. Something that in 2017 changed the way astronomers thought about the very shape of our cosmic motion. But that is the next part of the night. For now, drift a little. Let the Norma Cluster sit in your mind, huge and dim, half hidden in the dust. Let the 7 samurai and their 400 galaxies rest in the story where they belong. The 7 people who named the direction of our fall. Let the zone of avoidance be what it is. A curtain made of our own home, hiding the thing we are falling toward for the simple and humbling reason that we happen to live inside a spiral galaxy, and spiral galaxies come with disks, and disks come with dust, and dust blocks visible light, and the most important destination in our cosmic neighborhood happen to land directly behind the thickest part of it. Renée Kraan-Korteweg is still working on it. The H.I. Park's All-Sky Survey found things the optical telescopes missed. The 2-mass near-infrared survey found more. The X-ray surveys found more still. The Shapley Supercluster, 800 million light-years out, was still waiting to be found as recently as 2016. The map is not done. The census is still being taken. And the accounting problem, the fact that the Great Attractor's mass isn't quite enough to explain our speed, that the budget has a gap, that problem was already pointing elsewhere. Pointing outward to a larger and more distant structure that turns out to be an even bigger piece of the gravitational picture. Pointing toward Shapley. But also, and this is the part that changes everything, pointing towards something on the entirely other side of the sky. Not a pulling mass at all, something that works the other way, a vast region of almost nothing, a cosmic void so large and so empty that it exerts its own kind of influence on everything around it, the push from emptiness, the repulsion that isn't really repulsion at all, but might as well be. That discovery came in 2017, and it rewrote the story. So let us take a moment here, lying wherever you are, to register what we have already learned. The Great Attractor is real. The motion is real. The curtain of dust is real. And the Norma Cluster, Abell 3627, that dense knot of galaxies peeking through the zone of avoidance about 220 million light-years away, is real. And it is the closest thing we have to a face for whatever is pulling us. But here is the accounting problem. When you add up the mass in the Norma Cluster and the surrounding structure of the Great Attractor region, all the galaxies, all the gas, all the dark matter halos that astronomers can infer are wound around it, the numbers do not quite come out right. The mass is significant, the gravitational influence is genuine, but it is not enough. Not fully enough to explain why we are moving at 600 kilometers per second relative to the cosmic microwave background rest frame. Something is still missing from the ledger. There is more pull than the named attractor can account for, and that fact has been nagging at the edges of cosmology for decades now. The gap in the budget pointed outward, farther out, past the Great Attractor, past the Norma Cluster, past the Centaurus-Hydra region, where the 7 samurai found their streaming galaxies back in 1988. It pointed toward a structure so large and so far away that it dwarfs the Great Attractor the way a mountain dwarfs a hill. It pointed toward Shapley. The Shapley Supercluster, sometimes called the Shapley Concentration, named for the American astronomer Harlow Shapley, who first noticed an unusual density of galaxies in that region of the sky in the 1930s, sits roughly 650 million light-years away in the same general direction as the Great Attractor in the constellation Centaurus. And it is, by most measures, the single largest concentration of galaxies in the part of the universe we can reasonably survey. Not the largest structure in the observable universe at all scales. There are filaments and walls that cover larger distances. But in terms of sheer concentrated mass, close enough to influence our local motion, Shapley is the heavyweight in the room. Think of it this way: if the Great Attractor is a strong regional magnet, Shapley is a stronger, more distant one, aligned in roughly the same direction. The pull from both superimposes. And because Shapley is so much more massive than what the Great Attractor region alone can muster, analyses of the bulk flow, the coordinated streaming of galaxies across enormous volumes, suggest that a significant fraction of our 600 km per second motion is actually being driven by Shapley, not by the named attractor at all. Work by Michael Hudson and collaborators in 1999 and again in 2004 put firmer numbers on this. The Great Attractor is not the final answer. It is a waypoint, a foreground structure sitting between us and a deeper, more powerful gravitational center, which means the name is a little misleading and the story is a little more complicated than the headlines let on. The thing that is pulling our galaxy, our real destination in some sense, is not the thing most people picture when they hear the words Great Attractor. The Great Attractor is close and real and gravitationally important, but the larger pull, the dominant gravitational signature, appears to come from something 650 million light-years away that most people have never heard of. This is not a failure of science. It is a correction. It is the story of what actually happens when you keep looking, keep measuring, keep refining your model. The early picture, a single monster mass pulling us at 600 kilometers per second, was the best picture available with 1980s data. And then the data got better, and the picture got bigger, and the foreground feature turned out to be a waypoint rather than the destination. And the story got stranger, not simpler. Now, there is something else we need to talk about before we go any further, because it comes up almost every time the Great Attractor is discussed, and it deserves a clear answer. People sometimes ask whether this motion violates the expansion of the universe, whether it means we are somehow escaping the Hubble flow, whether the fact that our galaxy is moving at 600 kilometers per second toward a mass concentration means that the universe's expansion is being overcome locally by gravity. The answer is no, and the distinction is worth understanding because once you have it, the whole picture becomes cleaner. The Hubble flow is the overall expansion of space itself, the stretching of the fabric that carries all galaxies apart from each other, the recession that Edwin Hubble measured in the 1920s and that cosmologists have been refining ever since. It is not that galaxies are flying through space away from each other. It is that space between them is expanding, carrying them along. Peculiar velocities are something different. They are the motion of galaxies through space, the local gravitational tugs that make individual galaxies or groups of galaxies or clusters or superclusters move relative to each other in addition to the overall cosmic expansion. When astronomers measure the CMB dipole and find that the local group is moving at roughly 600 kilometers per second in the direction of the Centaurus-Hydra region, they are measuring our peculiar velocity, our motion through space, not with space. The gravitational attraction of the Great Attractor and the Shapley Supercluster is pulling us through the fabric of the universe, while the fabric itself is still expanding in all directions. These two things can coexist. The universe expands and galaxies also drift, pulled by local concentrations of mass. On the very largest scales, hundreds of millions, billions of light-years, the expansion wins. Gravity cannot overcome it across that much distance. But on more local scales, inside superclusters, inside the gravitational reach of structures like Shapley or the Great Attractor region, the peculiar velocities are real and measurable and significant. It is like a river with a current. The current is the Hubble flow, carrying everything along in the same general direction. But within the river there are also local eddies, whirlpools and backflows and regions where water is moving toward each other rather than apart. The peculiar velocities of galaxies are the eddies. They do not cancel the river, they ride on top of it. And the standard model of cosmology, lambda CDM as it is called, the model built on cold dark matter and a cosmological constant representing dark energy, predicts that exactly these kinds of peculiar velocities should exist. The Great Attractor, the bulk flow, the streaming of galaxies toward overdense regions, all of this falls within the expected range of what gravity does on large scales, within the framework of a universe that is also expanding. It is not a mystery in the sense of being unexplained. It is a quantitative puzzle. How much mass? How far away? In what configuration? But the existence of bulk flows is not surprising. It is, in fact, required by the physics. So, the motion is real. The pull from Shapley and the Great Attractor region is real. The Hubble flow is also real. They coexist. And now we come to the double invisibility. The two layered reasons why something we cannot see is not just a poetic phrase. It is literally, structurally, physically true in two completely independent ways. The first is the one we have already spent some time with: the dust, the gas, the crowded stars, the zone of avoidance, that band of sky comprising roughly 10 to 20% of the total celestial sphere, where the Milky Way's own disk stands between us and everything behind it. The Great Attractor sits almost exactly behind the thickest part of this curtain at galactic coordinates close to L equals 320 degrees, B nearly zero, as close to the galactic plane as a structure could be. Optical light cannot get through. It is absorbed and scattered by the interstellar medium of our own galaxy before it can reach us. And that is why Edwin Hubble noticed the zone at all back in the 1930s, when he was counting galaxies and found a conspicuous band of sky where they seemed to vanish. They had not vanished, we just could not see them. Radio waves can get through. Neutral hydrogen, the 21 centimeter emission line, one of the most useful frequencies in all of radio astronomy, passes through the dust as if it is not there. The H.I. Parkes All-Sky Survey, HIPAS, mapped the hydrogen in galaxies across the whole southern sky, including the Zone of Avoidance, and found galaxies that no optical telescope had ever seen. Near-infrared light does better than visible light because the dust grains that absorb and scatter blue and green and red visible photons are not as effective at blocking the longer infrared wavelengths. The 2-mass near-infrared survey, the 2-micron all-sky survey, found thousands of galaxies hiding behind the galactic plane that only revealed themselves in infrared. X-ray observatories found galaxy clusters glowing in high-energy light that also punches through the dust. All of this work, much of it reviewed and synthesized by Renée Kraan-Korteweg and Ofer Lahav in their 2000 survey of what they called the universe behind the Milky Way, gradually revealed the structure the Zone of Avoidance had been hiding. The Norma Cluster, the broader overdensity, the shape of the Great Attractor region. But even with all of that, even with radio and infrared and X-ray photons doing the work that visible light could not, there is a second invisibility. One that is not about dust at all, one that no wavelength of electromagnetic radiation can solve because it is not an electromagnetic problem. Dark matter. The Great Attractor's mass, the total mass of the Norma Cluster, of the surrounding structure of the Shapley Supercluster beyond it, is overwhelmingly dark matter, not a little bit, not a rounding error. According to the standard cosmological model, calibrated to measurements by the Planck satellite published in 2018, roughly 85% of all matter in the universe is dark matter. Only about 15% of matter is the ordinary baryonic kind. Protons, neutrons, electrons, the stuff that makes stars and planets and gas clouds and you. Everything we have ever directly detected, everything every telescope has ever seen or photographed or measured, is the minority, the trace, the foam on the surface of a very deep ocean. Dark matter does not emit light, it does not absorb light, it does not interact with electromagnetic radiation in any way we have been able to detect. We know it is there because of what it does gravitationally, because of the way it bends the paths of light, the way it governs the rotation of galaxies, the way large-scale structure in the universe only makes sense if there is far more mass than we can see. The Norma Cluster is held together by dark matter. The Shapley Supercluster's enormous mass is mostly dark matter. The Great Attractor's gravitational influence comes predominantly from matter we have never seen and cannot image with any telescope we have built. So the title of this video is true in two completely separate and stacked ways. We cannot see what is pulling us because our own galaxy's disk is in the way, and we cannot see what is pulling us because the thing doing the pulling is, by its very nature, invisible to any instrument that relies on light. Two different kinds of invisibility, two different physical reasons, both real, both apply simultaneously. That is not a rhetorical flourish. It is the actual structure of the problem. And now, because this map is still being drawn, we should pause on a discovery that most discussions of the Great Attractor skip over entirely because it happened only recently enough that it has not yet made it into the popular understanding of the region. A discovery made by Renée Kraan-Korteweg's team, announced in 2016 and published in 2017, that adds another massive structure to the picture, something enormous, something also hiding in the zone of avoidance, but farther out, about 800 million light-years away. The Vela Supercluster. The Vela Supercluster is named for the constellation in whose direction it lies. Vela, the sail, part of the old Argo Navis constellation that was once drawn as a ship. And like the Norma Cluster, like the Great Attractor region, like so much of what is gravitationally relevant to our motion through the universe, it is hiding behind the Milky Way's disk. The Zone of Avoidance claimed it for decades. Optical surveys could not see it. Only when radio observations began revealing galaxies in that part of the sky, and when Kraan-Korteweg's team made systematic spectroscopic measurements to determine distances and velocities, did the supercluster emerge from the dust. It is very large, perhaps 100 million times the mass of the Milky Way, possibly more. It sits at a distance of roughly 800 million light-years, which is significantly farther than the Shapley Supercluster at 650 million light-years, and both are far beyond the Great Attractor region at 150 to 250 million light-years. The Vela Supercluster may itself be contributing to the bulk flow, to the coordinated streaming of our region of the universe, though its precise influence on our motion is still being quantified. The discovery demonstrated something important. We are not done mapping. The Zone of Avoidance still harbors structures we have only recently found, and possibly others we have not found yet. This is worth sitting with for a moment because it is genuinely humbling in a quiet way. We have been building detailed models of the large-scale structure of the universe, of the distribution of mass, of the gravitational landscape that shapes our motion for decades, and as recently as 2016, a major supercluster, a concentration of galaxies massive enough to potentially influence how our entire local universe flows, was still unidentified, still waiting behind the Milky Way's curtain for someone with the right instruments and the patience to look. The accounting is still being done. The map has blank spaces on it. Some of those blank spaces are very close to where the most important things are. And that is the nature of doing astronomy from inside a galaxy. You are embedded in the very thing that blocks part of your view. You are the telescope and the obstacle simultaneously. There is an irony in that which never quite wears off, no matter how many times you consider it. So let us now take stock of what we have. Our local group, the Milky Way, Andromeda, and some 80 smaller galaxies bound to them by gravity, is moving at roughly 600 kilometers per second relative to the rest frame of the cosmic microwave background. We know this because the CMB itself, that faint glow of microwave radiation left over from the early universe, the afterglow of the Big Bang, looks slightly warmer in the direction we are heading and slightly cooler behind us, a temperature difference of about 3.36 millikelvin measured by the COBE satellite in the 1990s and confirmed by Planck in 2018. That asymmetry is our speedometer. The oldest light in the universe is telling us how fast we are moving and in which direction. The direction is toward the Centaurus-Hydra region of the sky, where the Zone of Avoidance hides most of what matters. The Great Attractor sits there, its core region best represented by the Norma Cluster, about 220 million light-years out. The Seven Samurai identified this in 1988 by tracking the streaming motions of some 400 elliptical galaxies, all flowing toward the same focal point. Astronomers have since probed the zone with radio waves, infrared light and X-rays, progressively revealing what the dust had been hiding. And yet the Great Attractor, despite its dramatic name, is not sufficient. Its mass, while real and significant, does not fully explain the speed at which we and hundreds of thousands of surrounding galaxies are moving. The budget has a gap, and that gap points farther out, toward the Shapley Supercluster at 650 million light-years. Work from the late 1990s and early 2000s, particularly by Hudson and collaborators, suggests that Shapley drives a substantial portion of the bulk flow. The Great Attractor, then, is more accurately described as a nearer concentration in the same general direction. A foreground waypoint, a significant but not dominant player in the gravitational landscape. The named attractor is not the real attractor. The real culprit is farther away and less famous, and the thing doing the attracting is largely invisible not because of dust, but because it is dark matter. 85% of matter, invisible to every electromagnetic instrument, pulling us at 600 kilometers per second through the fabric of an expanding universe that is simultaneously carrying us apart from everything else. Now, here is where the story turns. Here is where it gets genuinely unexpected. Here is the part that took decades to see, that required a completely different way of thinking about cosmic motion, and that arrived in the literature in 2017 and quietly rewrote what we thought we understood about why we are moving the way we are. For a long time, the working assumption was this: we are moving because something is pulling us. The Great Attractor, Shapley, overdensity in the direction of Centaurus-Hydra. Mass that we are falling toward, the way a ball rolls down a hill because the hill is there. That model is true as far as it goes, but it turns out to be only half the story, because there is something on the other side of the sky, in the direction exactly opposite to the Great Attractor, and in that direction, rather than a concentration of mass, a cluster, a supercluster, an overdense region, there is almost nothing. A vast region of space substantially emptier than the cosmic average. A void. And a void, it turns out, pushes, not in the sense that empty space reaches out and shoves galaxies. The physics is subtler than that and more elegant. In a universe where matter is distributed unevenly, clumped here, absent there, a region that is denser than average pulls its neighbors toward it, while a region that is less dense than average creates an imbalance. The galaxies around a void are being pulled by the mass on all sides, but less strongly from the void's direction than from any other direction, because there is less mass there. The net effect is that galaxies on the edge of a void tend to drift outward, away from it, toward the denser surroundings. From the perspective of anything near a void, the emptiness behaves as though it is repelling. It is not actually pushing anything. There is no force emanating from the empty space, but the net gravitational effect, with the imbalance, functions like a push. Gravity from absence. The whole matters as much as the mass. In January 2017, Yehuda Hoffman, Daniel Pomarède, Brent Tully, and Hélène Courtois published a paper in Nature Astronomy identifying exactly this structure on the opposite side of the sky from the Great Attractor. They called it the Dipole Repeller, not because it literally repels, it does not, but because it sits on the opposite end of the dipole from the pull, and its effective influence on our motion is repulsion. A vast underdense region, a cosmic void of remarkable size, pushing us away from it and toward the Centaurus-Hydra direction in roughly equal measure to the pull from Shapley and the Great Attractor. Roughly half our motion is a push from emptiness, half is a pull from overdensity. The two work together, aligned by the coincidence, or perhaps the structure, of large-scale cosmic architecture. This is the part that changes everything, because for all of the decades of studying the Great Attractor, for all the work of the Seven Samurai and the radio surveys, and the infrared mapping and the X-ray observations, the working picture had always been, we are being pulled. The question was only what was doing the pulling, and how far away it was, and how much it weighed. The Dipole Repeller paper was the first time the opposite side of the sky was brought into the accounting as an active contributor. Not just the absence of pull, but the effective presence of push. Half push, half pull. And we had been telling half the story for 30 years. This is what good science does, eventually. Not with a dramatic announcement and a press conference, but quietly, in the pages of a journal with careful reconstructions of the galaxy velocity field. Tully and Courtois and Hoffman and Pomarède had been building the tools to do this kind of mapping for years, and the Dipole Repeller result came from the same framework they had used to define Laniakea in 2014. Map the flows. Find the basins and the ridges. Follow the water. And when they followed the water all the way, they found not just the basin we are draining into, but the high ground we are draining away from, which brings us naturally to Laniakea and to the question of where we actually live. Because the Great Attractor is not just a thing being pulled toward, it is a center, a focal point, and the thing it is the center of is our cosmic home at a scale so large that it makes the Milky Way feel like a single raindrop in a river. In September 2014, Brent Tully, Hélène Courtois, Yehuda Hoffman, and Daniel Pomarède published a paper in the journal Nature that redefined our address in the universe. The paper was titled The Laniakea Supercluster of Galaxies. And what it described was not just a new structure, it was a new method of defining structure, a new way of answering the question, where does one supercluster end and another begin? The traditional answer had been to draw boundaries based on the density of galaxies. Where the galaxies thin out, you have reached the edge. But Tully's team proposed something more physically meaningful. Define superclusters by the flow of galaxies. Map the peculiar velocities of tens of thousands of galaxies. Find the places where flows converge, where galaxies from all directions are streaming inward toward a common center, and call that a supercluster. Find the places where flows diverge, where galaxies on opposite sides of a boundary are flowing away from each other, each toward a different center, and call those the edges. It is a watershed method, exactly like hydrology. Trace the direction water flows on a landscape, find the ridges where rainfall divides into different river systems, and those ridges are the basin boundaries. Tully's team did this for the galaxy velocity field, finding the ridges in the cosmic flow, the great divides between different gravitational basins. And when they did, they found that the Milky Way, the local group, the local supercluster, that had previously been called Virgo Supercluster, all of us, sit inside one enormous basin. A flow that spans roughly 520 million light-years across, containing approximately 100,000 galaxies, with a total mass on the order of 10 to the power of 17 solar masses, 100 million billion times the mass of our Sun. A structure so large that traveling across it at the speed of light would take over 500 million years. They named it Laniakea, Hawaiian for immense heaven. Lani, heaven, sky. Akea, spacious, immense. The name was chosen in collaboration with Noah Napoleon, a professor of Hawaiian language, to honor the tradition of Polynesian navigators who crossed the Pacific Ocean using the sky as their map, reading the stars with a precision and intimacy that allowed them to find specks of land in the world's largest ocean. It felt fitting, Tully's team said, to name our cosmic home after the sky those navigators knew so well. Laniakea is our supercluster. Not the Virgo supercluster, which is a smaller region near the center. The Virgo cluster and its immediate surroundings, not just the local group, Laniakea. 100,000 galaxies, all of them flowing toward a common gravitational center. All of them draining like water in a bowl toward the lowest point of the basin. And the lowest point, the gravitational focal point, the bottom of the basin, that is where the Great Attractor sits. The Great Attractor is not a separate thing from Laniakea. It is Laniakea's center. The Norma Cluster, the surrounding overdensity, the Centaurus-Hydra region, all of it is the gravitational drain toward which all of Laniakea flows. When you say we are falling toward the Great Attractor, you are also saying we are falling toward the center of our own supercluster. These are the same statement now that we have the framework to see it. On the other side of Laniakea's edge, across the Great Divide, which is what the boundary ridge is sometimes called, sits the Perseus-Pisces supercluster, a different basin. Galaxies on that side of the divide flow toward the Perseus-Pisces center rather than toward Laniakea's center. The galaxies on the two sides of that ridge are, in a sense, flowing away from each other, each pulled toward its own gravitational home. They are the neighbors that drain toward different rivers. The great divide in the cosmic watershed. It is worth holding that image for a moment. The universe at these scales is not a uniform fog of galaxies. It is a landscape. It has valleys and ridges, high ground and low ground, flows and divides. And what Tully's team did in 2014 was to read that landscape for the first time. Not from the distribution of light, which depends on where galaxies happen to be visible, but from the direction of motion, which reveals the underlying gravitational terrain regardless of what dust might be blocking the view. The zone of avoidance cannot hide the flows. You can detect the peculiar velocity of a galaxy even through the Milky Way's disk, because Doppler shifts work in radio and infrared just as they do in optical. When Tully and his collaborators reconstructed the velocity field, they could trace the flow of galaxies on both sides of the zone, and the Great Attractor emerged not as a mysterious unseen blob, but as the bottom of a vast gravitational bowl that we call Laniakea, the Hawaiian name for our supercluster. Immense heaven. It is rather beautiful, actually, that this structure, defined by the invisible flow of 100,000 galaxies, centered on a region our own galaxy was blocking from view for decades, ended up named after the sky. And yet, and yet the picture was still incomplete. Because here is what nobody had quite said out loud, even after Laniakea was mapped and named, and the Great Attractor was reframed as a basin rather than a monster. The question everyone assumed they understood, what is pulling us, had been carrying a hidden assumption all along, the assumption that we were being pulled, only pulled. For decades, the entire conversation about our peculiar motion was framed as attraction. Something over there is tugging us toward it. Find the something, quantify the mass, explain the speed. That was the model. That was the shape of the investigation. And it was half wrong. In January of 2017, a paper appeared in Nature Astronomy. The authors were Yehuda Hoffman, Daniel Pomarède, Brent Tully, and Hélène Courtois, the same team, more or less, who had given us Laniakea 3 years earlier. And what they described was something that should, in hindsight, have been obvious. But it wasn't. It took careful analysis of the same velocity fields, the same peculiar motion data, to see it clearly, to name it. They called it the Dipole Repeller. Take a moment with that name because it contains a whole physics lesson folded into 2 words. A dipole is something with 2 poles, a positive and a negative, a push and a pull. We had known about the pull side for decades, the Great Attractor, Shapley, the overdense regions drawing us in, but the dipole is symmetric. If there is a direction toward which we are moving, there is a direction from which we are moving away. And on that opposite side of the sky, what did Hoffman and his colleagues find? Nothing. Almost literally nothing. A vast underdense region, a cosmic void, an absence of galaxies far larger and emptier than would be typical in the universe's large-scale structure. And that absence, that void, was pushing them. Now, the word pushing needs a little unpacking because gravity does not literally push. Gravity attracts. But here is the thing about a void. The regions around a void are denser than the void itself. So the matter in those surrounding denser regions is pulling you away from the void toward themselves. From your perspective, sitting inside the void or near its edge, it feels like a push, like you are being repelled by the empty region. The net gravitational effect of a large underdensity is to move nearby matter away from it toward the denser surroundings. It is repulsion by default, not because the void is pushing, but because everything else is pulling you away from it. Imagine being inside a circle of people who are all leaning away from you toward their own distant friends. Nobody is shoving you, but the net effect of all that distant attraction pulling all your companions away from the center leaves you effectively displaced outward. The void does something similar, but at the scale of hundreds of millions of light years. The Dipole Repeller sits on the opposite side of the sky from the Great Attractor and Shapley. We are flowing away from it and toward them. And according to Hoffman, Pomarède, Tully, and Courtois, the contribution of this repulsion to our total peculiar velocity is not trivial, not a footnote. Roughly half of our 600 kilometers per second motion is a push from this vast emptiness. Half. Think about what that means. All those decades of measuring bulk flows, looking for enough mass on one side of the sky to explain our motion. The reason the numbers kept not quite adding up, the reason the Great Attractor's mass seemed barely sufficient, the reason even Shapley at 650 million light-years still left some motion unaccounted for. Part of the reason was that people were only looking at half the equation. They were searching for the pull and not accounting for the push. The Dipole Repeller completed the picture, or at least brought it much closer to complete. We are not simply falling toward a gravitational basin, we are falling toward it and being pushed from behind simultaneously. A cosmic tug-of-war in which one team is pulling us forward with mass, and the other is, in the most indirect, gravitational by absence sense, nudging us from the rear. It is strange to think about. We do not feel it. There is nothing in your body's experience, nothing in the night sky visible to the naked eye, nothing in any sensation available to human perception that hints at this. And yet the oldest light in the universe, the cosmic microwave background, that faint afterglow of the Big Bang itself, now stretched into microwaves and diffused across every direction, encodes this motion precisely. The temperature asymmetry in that ancient radiation, 36 millikelvin warmer in one direction and correspondingly cooler in the opposite, is the fingerprint of both the pull and the push combined. It does not distinguish between them directly, but it registers their total effect with extraordinary precision. We are moving. We know exactly how fast. And now, in 2017, we knew that the motion is driven by two complementary gravitational realities, the richness ahead and the emptiness behind. So let us return to Laniakea, because the Dipole Repeller and Laniakea are really two sides of the same revelation, and understanding one deepens the other. Our Brent Tully and his collaborators, Hélène Courtois, Yehuda Hoffman, and Daniel Pomarède, published their map of Laniakea in Nature in September of 2014. And what they had done, technically, was reconstruct the gravitational velocity field of the local universe from observations of about 8,000 galaxies whose peculiar velocities had been measured. Using a mathematical filtering method, they smoothed and extrapolated those velocities across the surrounding volume of space and identified the underlying flow structure. What they found was that roughly 100,000 galaxies spread across a region about 520 million light-years in diameter are all flowing slowly over billions of years toward the same gravitational focus, toward the same bottom of the same basin. And that basin, that focal point, is the Great Attractor region. Think of it like water, not like a single waterfall, but more like an enormous shallow landscape after rainfall. Water does not know in advance where it is going to flow. It simply responds to gravity, to the shape of the terrain beneath it. It follows the lowest path. 1,000 rivulets on a hillside will converge into streams. Streams will converge into rivers. Rivers will converge at the lowest point of the basin, not because anyone told them to, because that is what gravity and terrain together produce. This is the watershed method. This is how Tully's team defined Laniakea. Not by asking where the galaxies are, their positions can be hard to read through dust, but by asking which way they are moving. Flow lines traced backward converge on the Great Attractor region. Everything upstream of a particular ridge drains to the same side. That ridge, that crest beyond which the flows begin heading in a different direction, is the boundary of Laniakea. Our home, then, is not a circle, not a sphere with a clean edge. It is a watershed, an irregular, extended region of space defined by a shared gravitational destiny. 100,000 galaxies, each one enormous, each one containing hundreds of billions of stars, all drifting on the same slow journey toward the same gravitational valley. And we, the Milky Way, are one of them, sitting on the outer edge of Laniakea, far from the center, but still, unmistakably, flowing inward, flowing toward the Great Attractor, toward the basin's lowest point. The mass of Laniakea is staggering, roughly 10 to the power of 17 solar masses. That is 100,000 trillion times the mass of our Sun, a number so large it is essentially decorative. It conveys scale without landing as an image. So let us try it differently. The Milky Way is thought to contain somewhere between 100 and 400 billion solar masses of ordinary and dark matter combined. Laniakea's mass is roughly 100 million times that, 100 million Milky Ways, give or take. That is what we are inside, and the name, Laniakea. It is Hawaiian, chosen in collaboration with Nawa'a Napoleon, a professor of Hawaiian language at Kapiolani Community College in Honolulu. In Hawaiian, lani means heaven or sky, the elevated, the celestial. And Akea means spacious, immense, broad, immense heaven. The name honors the Polynesian navigators who, centuries ago, crossed the Pacific using nothing but the stars, the swell of the ocean, and an intimate understanding of the sky above them. They navigated by what they could see and feel and read in the natural world. It is, Tully's team noted, a fitting legacy for people whose descendants now help name the largest structures in the observable universe. There is something quietly moving about that. The same sky that guided canoes across thousands of miles of open ocean also carries, encoded in its oldest light, the signature of a supercluster structure so vast that it took radio telescopes, infrared satellites, and decades of peculiar velocity catalogues to reveal it. Now, there is something important to hold alongside the wonder of Laniakea, and it is this. Laniakea is not a permanent object. This matters. When you hear that our galaxy is part of a supercluster 520 million light-years across containing 100,000 galaxies, all flowing toward the same center, it is natural to picture a structure that will eventually collapse, that will, over billions of years, merge and condense into one enormous gravitationally bound mass. But that is not what is going to happen, because of dark energy. You may remember the two kinds of invisible that we have been carrying through this story: the dust of the Zone of Avoidance, which hides the Great Attractor from optical telescopes, and the dark matter, which makes up about 85% of the matter that is doing the gravitating, and which is invisible to every wavelength of light we know how to detect. There is a third invisible force at work, and it operates at a different scale entirely. Dark energy is the name we give to whatever is driving the accelerating expansion of the universe. It is not a substance you can find in any one place. It is a property of space itself, or seems to be. And as the universe expands, the influence of dark energy grows relative to the influence of gravity. On small scales, the scale of galaxies, galaxy clusters, even the local group, gravity wins. The Milky Way and Andromeda are gravitationally bound to each other and will eventually collide and merge roughly 4 to 5 billion years from now, forming what astronomers sometimes call Milky Way. That is a local event, an internal affair of the local group, entirely separate from the large-scale flow toward the Great Attractor. Two things can be true at once. We are drifting on the vast flow toward Laniakea's basin, and simultaneously, on a much smaller scale, our nearest large neighbor is falling toward us. Scales matter. But on the scale of Laniakea, 520 million light-years, dark energy wins. The mutual gravitational attraction of those 100,000 galaxies is not strong enough to overcome the accelerating expansion of space. Laniakea is not gravitationally bound. It will not collapse. Instead, over cosmic time, the expansion of the universe will eventually pull its constituent galaxies apart. The flows that define Laniakea today will, in the far future, be erased. Galaxies on opposite edges of the supercluster will recede from each other at speeds that eventually exceed the speed of light, not because they are moving faster than light through space, but because the space between them will be expanding faster than light can cross it. So we are flowing toward a valley we will never reach. The flow is real. The motion is real. We are genuinely drifting toward the Great Attractor at hundreds of kilometers per second, but we will not arrive. Long before we could cover that distance, long before the Milky Way and its local group could travel anything close to 150 or 250 million light-years to the Norma Cluster, the universe's expansion will have reshaped the landscape entirely. The basin's walls will have spread apart. The river's destination will have moved beyond reach. There is something in that worth sitting with for a moment. not sadness exactly. More like the feeling of realizing that a journey you thought was leading somewhere was never really about the destination at all. We are carried by a flow toward a focal point that the universe itself will never let us reach. We are part of a structure that is defined by its motion, not by any eventual convergence. Laniakea is not a place we are going to. It is a shape our motion makes, and the edge where Laniakea ends, the Great Divide, is equally real and equally quietly astonishing. On the other side of that ridge, the flows point away from us. The Perseus-Pisces supercluster lies beyond the divide, and the galaxies on that side are draining toward their own gravitational basin, not ours. They are our cosmic neighbors in the most abstract sense, close enough on the universal scale to be in the same general neighborhood, but each pulled by its own different river system. The boundary between Laniakea and Perseus-Pisces is one of the largest coherent features in the universe's large-scale structure. A ridge line in the cosmic watershed millions of light-years long, separating two vast drainage basins. Now, there is a piece of honest accounting that belongs here, because this whole story has been about being honest with what we know and what we do not. The mass of the Great Attractor and of Laniakea as a whole has been a moving target. The earliest estimates from the late 1980s and early 1990s imagined something like tens of thousands of Milky Way masses concentrated at a single point. Those early numbers were large and dramatic, and it turned out somewhat misleading. As the picture came into focus, as the Norma Cluster was identified, as radio and infrared surveys penetrated the Zone of Avoidance, as Shapley was recognized as a major contributor, as the full Laniakea velocity field was mapped, the original single monster picture was replaced by something more extended and more subtle. The mass estimates were revised, spread across a larger volume, redistributed between the Great Attractor foreground and the more distant Shapley region. The concentration at one point dissolved into a landscape. This is how science actually works, not a single revelation and then certainty, but successive approximations. Each generation of data revises and refines what the previous generation saw. There is also a genuine open question at the edges of this story, and it deserves to be named honestly. Some studies of bulk flows, the large-scale coherent motion of galaxies, have found evidence that the flow might be slightly larger than the standard cosmological model LCDM predicts it should be. LCDM, which stands for lambda cold dark matter, is the model that describes the universe as containing ordinary matter, cold dark matter, and dark energy, the lambda term, in proportions consistent with what the Planck satellite measured in its 2018 Cosmological Parameters release. According to LCDM, there is a prediction for how large the peculiar velocities of galaxy clusters should be on different scales. Some measurements of the bulk flow on very large scales have come in slightly above what LCDM predicts. Others find consistency. This is not a crisis, it is a question at the frontier of measurement. The data are difficult. Measuring peculiar velocities across hundreds of millions of light-years requires very careful calibration, and different surveys using different methods have reached different conclusions. The community is working on it. If a genuine tension emerges between the measured bulk flow and LCDM's predictions, it would be scientifically interesting. It would point toward some refinement of our cosmological model, but it would not overturn the picture we have been building tonight. It would be a fine-tuning at the edges. There is also something that bears a careful mention, because you may encounter it if you go looking. A 2008 claim by Alexander Kashlinsky and colleagues, based on the motion of galaxy clusters as seen through the cosmic microwave background, that there is a dark flow on scales much larger than the Great Attractor, a coherent motion of matter across billions of light-years, possibly hinting at structure outside the observable universe. It was a striking claim. It was also largely not confirmed. The Planck satellite's analysis found no robust evidence for dark flow. The broader scientific community has not adopted it. It remains a disputed and largely set-aside result. It is not part of the verified picture. It is worth knowing exists because it illustrates that the large-scale structure questions are still live and researchers are still pressing at them. But it should not be mistaken for established science. The established picture, the one built from CMB dipole measurements, from peculiar velocity catalogues, from HIPAS and TUMAS and the Norma Cluster, and the Shapley Supercluster, and the Dipole Repeller, and the Laniakea velocity field, is extraordinary enough on its own. It does not need the support of contested claims. And here is the reassurance that perhaps some part of you has been quietly waiting for, because these questions have a way of producing a low-level unease, even in the calmest of listeners. Is any of this dangerous? Are we racing towards something that will harm us? No, not remotely. The motion of our galaxy toward the Great Attractor is not a collision course with a single massive object. There is no object to collide with. The Great Attractor region is not a point. It is a vast, diffuse gravitational landscape containing many galaxies spread across many millions of light years. We are drifting toward it the way water drifts toward the low point of a shallow basin, and we are doing so at 600 kilometers per second, which sounds fast, which is fast, genuinely faster than almost anything on a human scale, but which is vanishingly slow compared to the distances involved. At 600 kilometers per second, it would take us something like 100 billion years to cross the distance to the Norma Cluster, even if we were heading straight for it. The universe is only about 13.8 billion years old. Long before any such journey could be completed, the Sun will have expanded into a red giant and our Earth will be gone. Long before that, the accelerating expansion of space will have reshaped the entire cosmic landscape. We are not in danger. We are simply participants. One small galaxy among 100,000, all flowing together in a pattern so vast it took the better part of a century to detect. And the map is still being drawn. In 2016, a team led by Renée Kraan-Korteweg, the same researcher who has spent decades pioneering the exploration of the Zone of Avoidance, announced the discovery of the Shapley Supercluster. It lies roughly 800 million light-years away, also partly hidden behind the Milky Way's disk, also waiting in the obscured regions where dust and stars conspire to block our optical view. The Shapley Supercluster is massive. It may be contributing to the bulk flow of galaxies in our region. It was found only a few years ago using techniques developed specifically to see through the Zone of Avoidance. The same radio surveys, the same near-infrared observations, the same patient mapping of neutral hydrogen at 21 centimeters that first revealed the Norma Cluster and began to flesh out the Great Attractor region. Think about what that means. We are not looking at a completed map. We are in the middle of a survey that is still turning up major features. The Shapley Supercluster was invisible to us until very recently, not because it is distant and faint, but because our own galaxy was blocking it. There may be more. The Zone of Avoidance is not a blank space in the universe. It is a blank space in our knowledge of the universe, slowly being filled in as our instruments improve and our techniques grow more sophisticated. Kraan-Korteweg's career has been, in a sense, dedicated to that slow filling in. The Universe Behind the Milky Way, as the title of a review paper she co-authored in 2000, is a real place, full of real structure, full of galaxies that have been tugging at us all along without our knowing what they were. Every decade brings new surveys, new detections, new revisions to the picture of what is out there in the hidden zones. The Great Attractor story is not finished. It is ongoing. Each generation of astronomers inherits a slightly more detailed map and leaves a more detailed one for the next. So let us step back now. Let us step a long way back. You are lying somewhere quiet. Perhaps it is late. Perhaps a lamp is still on in the corner, the light soft and steady. Outside, if you were to go outside and let your eyes adjust, you might see the faint smear of the Milky Way crossing the sky. The disk of our own galaxy, seen edge on from inside, a river of starlight. That river of light is also, as we have discussed, the zone of avoidance, the very thing that hid the Great Attractor from view for so long. The beauty and the obstruction are the same object. Behind that band of light, in the direction of the constellation Centaurus and into the Hydra region, is the gravitational focal point of the largest structure we belong to, the bottom of Laniakea's basin, the place toward which 100,000 galaxies, including ours, are drifting slowly on a journey we will never complete. And on the opposite side of the sky from that focal point, there is an enormous emptiness, a vast underdense region, the Dipole Repeller, nudging us from behind with the gravity of its own absence. You are right now in motion, not because of any engine or explosion or deliberate act, simply because of gravity, simply because the universe has structure, hills and valleys, voids and clusters, and structure means flow. You are part of the flow. The atoms in your body are part of the flow. The Earth is part of it, and the Sun and the Milky Way's 400 billion stars and the local group's 80-odd member galaxies. All of it drifting together, carried by the same slow current in the same direction, at the same 600 kilometers per second. That speed is measured by the oldest light in the universe, the cosmic microwave background, the afterglow of the Big Bang, emitted when the universe was only about 380,000 years old, now stretched and cooled into microwaves, is the most ancient observable thing. It surrounds us in every direction. It is, in a sense, the background against which all motion in the universe can be measured. And in that background, our motion shows up as a faint asymmetry, a warmth of 3.36 millikelvin in the direction we are heading, a corresponding coolness behind us, measured first by COBE, confirmed with exquisite precision by Planck, a thermometer reading of our place in the cosmic flow. What the seven samurai detected in 1988, Lynden-Bell, Faber, Burstein, Davies, Dressler, Terlevich, and Wegener, studying 400 elliptical galaxies and finding them all streaming the same way, was real. The Great Attractor they named was real, even if the picture of what it is has grown considerably more nuanced. The flow is real, the watershed is real. Laniakea is real, even though it is defined by motion rather than by light, even though it carries a Hawaiian name honoring navigators who read the sky with their eyes and their bodies and their centuries of accumulated knowledge. And the invisibility is real, and it is layered. Our own galaxy's dust hides the Great Attractor from optical observation. The matter doing most of the gravitating, the dark matter that makes up approximately 85% of all matter in Laniakea's mass budget, is invisible to every wavelength of light we know how to use. We are pulled towards something we cannot see by forces we cannot directly observe on a journey we will never complete as part of a structure that will eventually be dissolved by dark energy long before it can collapse. This is not a story of mystery unsolved. It is a story of mystery progressively resolved, not into simplicity, but into something stranger and more specific and more true. The Great Attractor is not a monster. It is a basin. Laniakea is not a wall of mass. It is a shape that flowing galaxies make. The Dipole Repeller is not a hole. It is an absence whose gravitational consequences are as real as any presence. The picture is more honest than the one people started with. Less dramatic, perhaps, in the way of science fiction, but far more astonishing in the way of reality. And here is the quiet thing that I find myself returning to when I think about all of this late at night. In 1929, Edwin Hubble was counting galaxies and noticed the strange blank band across the sky, the zone of avoidance, the region where galaxies seem to thin out and vanish. He mapped its outline. He did not know what was hiding there. He could not see through the dust. 60 years later, 7 astronomers measured the motions of 400 galaxies and heard, in those motions, an echo of something massive pulling from behind the curtain. They could not see it directly, but they could hear it in the data. They named it, even without seeing it. Another 6 years after that, radio astronomers and infrared surveyors began to see through the curtain, not with light that could be stopped by dust, but with wavelengths long enough to pass straight through. And they found the Norma Cluster. Abell, 3627, a glimpse of the Great Attractor's visible core peeking out from behind the obscuring veil of the Milky Way's plane. And then in 2014, a team of 4, Tully, Courtois, Hoffman, Pomarède, drew the shape of our cosmic home, not from the light of galaxies, but from the direction of their motion. 100,000 galaxies all drifting together, forming a structure they named after the sky that guided Pacific navigators across an ocean. Immense heaven. And then in 2017, the same team looked at the other side of the equation and found the push, the emptiness driving us forward, the void, the Dipole Repeller. Each step was made possible by the previous one. Each answer opened a deeper question. Each tool that let us see a little further, through dust, through distance, through the indirect evidence of motion and temperature, revealed that the universe is larger, more structured, and more surprising than the previous tool had suggested. This is what the Great Attractor story is, underneath the mystery of the weak framing. It is the story of how science extends human senses, how we learn to read the temperature of ancient light as a speedometer, how we learn to use the 21-centimeter wavelength of neutral hydrogen as a kind of sonar for mapping the hidden universe, how we learn to treat the direction of motion as a map of the terrain, how we learn to find a void by its gravitational shadow. Every tool built on the one before, every generation of astronomers inherited a question they didn't fully ask and answered it well enough to see the next one. The map is not finished. The zone of avoidance still holds secrets. The Shapley Supercluster was found only in 2016, and there may be more structures waiting in those obscured regions. The question of whether our bulk flow is fully consistent with the Standard Cosmological Model, LCDM, remains open at the edges. The interplay of the Dipole Repeller and the various overdensities, Shapley, Norma, the extended Great Attractor region, is still being worked out with improving data. But the framework is there. The shape of the answer is known even if every detail is not yet filled in. We live in a galaxy that is part of a local group, that is part of a flow, that is part of a supercluster named Laniakea, that is defined by the direction 100,000 galaxies are drifting, that is centered on a gravitational basin called the Great Attractor, that is driven by both a pull from overdense regions ahead and a push from an underdense void behind, that will never arrive because dark energy will dissolve the structure long before any gravitational collapse could occur. That is the honest, complete, true answer to what is pulling our galaxy towards something we cannot see. And the most human part of all of it, I think, is this. We found it by listening, not looking, by measuring the motion of distant galaxies, by reading the temperature of ancient light, by asking which way things are flowing rather than where they happen to be at this moment. We found our cosmic address in a watershed defined not by any visible wall, but by the direction in which 100,000 galaxies are quietly, imperceptibly, unstoppably moving. We are made of the same matter as all of it. The dark matter that fills Laniakea and supplies most of its gravitational pull is, in a sense, the same category of stuff that may constitute a large fraction of the universe's mass budget, including whatever dark matter halo surrounds our own Milky Way. The ordinary matter, hydrogen, helium, carbon, oxygen, the atoms in your body, was forged in stars that live inside these same vast supercluster structures. You are not separate from the cosmic flow. You are an eddy within it, a small, local, temporarily coherent arrangement of matter that is itself part of the larger pattern. You are a piece of Laniakea. You are flowing right now at 600 kilometers per second. You cannot feel it. There is no wind, no sensation of motion, no physical sign, but the oldest light in the universe knows. It is 336 millikelvin warmer in one direction than the other, and that tiny thermal whisper is the trace of your passage through space. Wherever you are right now, and I asked that question at the very beginning of tonight, didn't I? Wherever you are listening from, whatever time it is in your corner of the world, your coordinates in this vast and flowing cosmos are the same. On the outer edge of Laniakea, in the Milky Way, in the local group, on a planet orbiting a middle-aged star, in a galaxy that is drifting on the same slow river as 100,000 others toward a valley it will never reach, in a supercluster whose name means immense heaven. That is where you are. That is where we all are. I hope there is something restful in that rather than something overwhelming. The scale is too large to worry about. The time scales are too enormous to fit inside any human anxiety. The Great Attractor is not coming for us. We are moving towards it the way clouds move, slowly, in response to gradients we did not choose, as part of a pattern far larger than ourselves. It is not threatening. It is simply the shape of where we live. And the scientists who found it, the Seven Samurai in 1988, with their catalogue of 400 galaxies, Renée Kraan-Korteweg and her colleagues spending years developing techniques to see through the zone of avoidance, Tully and Courtois and Hoffman and Pomarède drawing watershed lines through the velocity field of 100,000 galaxies. The same team looking at the opposite side of the sky in 2017 and finding the void that is pushing us. They are, in their way, doing what the Polynesian navigators did, reading the invisible patterns, finding their position not by landmarks but by the direction of flow. The sea doesn't offer handholds, neither does space, not in any direct sense, but both reward close attention. Both yield to people who ask the right questions with the right patience and the right instruments, whether those instruments are stars and ocean swells or radio telescopes and CMB satellites, and both lead eventually to answers that are more beautiful and stranger than the questions that started them. The Great Attractor is not a monster. It is the lowest point in the landscape of the local universe, and we are part of the rain that falls toward it. If you've enjoyed drifting through all of this tonight, through the dipole in the ancient light, and the hidden dust of the Zone of Avoidance and the Seven Samurai, and the flowing rivers of 100,000 galaxies, and the push from empty space, a quiet like and subscribe would mean a great deal to this small channel. Small creators like me truly rely on your support to keep these slow nights going. And if you'd like to leave a comment, I would genuinely love to know, where in the world are you listening from tonight, and what time is it in your corner of the universe? Sleep well, wherever you are. The flow will carry you. It always has. Close the books, dim the lamp. Class is over, sleepy scholar.